What we'll do now is explore a new scenario wherein we can free a memory region twice, and what would happen because of that. And as a stepping stone towards that phenomena, we'll also try and understand how might malloc be working, right? So working of malloc, and again, this is, oops, yeah, this is working of malloc, and this is an approximate working based on, some implementation that I knew, and kind of I also implemented malloc for one of the embedded systems application way back in time. Um, and my kind of explanation here is based on how I implemented it. This might differ from the standard Linux implementation. That's the point. So first off, we call like a memory region heap. So in this case, let's say 10 MB, right? So the way malloc allocates memory is, um, first of all, the heap management systems needs to be told how many bytes, right? And then the question is, when we call free, we only pass the pointer, right? So we only pass the pointer p, and it is supposed to figure out how many bytes were allocated. So let's just first talk about that. So what we'll now do is we'll understand how malloc, after the memory allocation is done or during the memory allocation, how does it keep track of the number of bytes it's giving away. And the way malloc works then is, okay, let's assume that this is our memory pool, and what I'm going to do is each brick here is now 1 byte, and the address is going this way as well as this way. So we go from 0 to some 100 here, 1024, let's say, and then we start from 1025 um, from the second row, right? So we are seeing memory as a grid now, and kind of life becomes simpler in this model. Everything else remains same. Instead of just, having it top down now, I'm having it in chunks. Okay, so that's that. And right, so we allocated, let's say, and each one of these is 1 byte, right? Okay, let's say I allocated 4 bytes, right? 4 bytes. So I was to get from somewhere 4 bytes, right? I was to get these 4 bytes, let's say. So I would be returned this address, this address. What malloc will do is it'll actually allocate 4 more bytes, right? So it'll allocate 4 more bytes here. It will give me the pointer to this, so it'll return 1025. So 1025 is what I get. And what it'll do is just behind the 1025, the 4 bytes, it'll store the number 4 there. So essentially, it gives me this chunk and then allocates 4 bytes behind, and there it will store the size. And this width here, the how many bytes extra to allocate, that comes from the size underscore t, which happened to be an int. So you take the size of int, which happens to be 4, right? So had this been not int but long, then it would have allocated 8 bytes extra. And so it is keeping the information about how much memory area to free here, right? Okay. So 4 bytes here are allocated now, and 4 bytes here are storing the size 4. Now what I do is I call free and then say, hey, take this pointer. So I'm essentially returning it this 25, no, not 25, 1025, this number. So the heap allocator, the mechanism which is handling the memory allocation, it gets to know, okay, you have given me 1025. I must go back 4 bytes to figure out how much of the region I had allocated for you earlier, right? So then in that case, it will reclaim back this much memory region. This is how it normally works. Now what we are going to do is we are going to say, okay, P is equal to, and I'll skip, well, let me not skip. Why add confusion? And also it's not necessary that everything be int here. Let me just get rid of all of this. We can also have this, right? A character pointer P, and then all you have to do is character pointer malloc, and let's say 10241 KB worth of memory, right? So in the space here, where 4 bytes, let's say this is 4 bytes now. So 1024 is being stored here, and starting from the next address, that's what P is. So P is, let's say, XYZ, right? X, Y, and Z. Okay, so we did a lot of work here. Then we said free P. Very nice. So all of this space here now, let's say this was whatever 1 KB. So all of this space 1 KB plus 4 bytes is now returned back to heap. Nice. Now what happens is you do again something similar, Q, something similar to this, that is, and then you ask for, let's just say another 1 KB, right? Or let's say you ask for who knows, 2 KB, right? And as luck would have it, you know, you are given 4 bytes, well, 4 bytes for the bookkeeping. So 1024 into 2, that number is stored here. And starting from this address to somewhere here, the 2 KB is pointed to by Q now. Okay. And let's say, you did some work with Q. So this memory region is populated, a lot of data is available there. And for whatever reason, this number happens to be 4 GB now, right? 4 GB. Exactly this box here, right? Which was earlier the 4 bytes right behind the XYZ address that P was holding, right? And then after this, there are, memory allocations for some other dynamically allocated regions, so on and so forth. But this 4 GB, this number, some random integer value that happens to be here because of the manipulation done on the region of Q, the memory, the 2 KB region that we fiddled with here, somehow this 4 number equivalent to 4 GB landed here. Now accidentally, the programmer unknowingly, because code has a lot of lines, people have different things that they're doing, blah blah blah, somehow we end up doing a free P again. Now imagine what happens. P is holding XYZ. So we tell the heap allocator, hey, go to the XYZ, step back 4 bytes, and figure out how much you have allocated me. It's not keeping a track of am I seeing a free twice of the same memory region of the same allocation? It doesn't keep track of that. So the heap allocator would be like, yeah, okay, XYZ, go to XYZ, step back 4 bytes, read, and it reads the number 4 GB. Now there is a problem. And the problem is that all of this memory region would be considered free, meaning uh, in the heap allocate or heap or the memory allocator now, next time somebody asks for an allocation, let's say there was I don't know, ABC pointer ABC, which was like, hey malloc, give me 4 KB, right? And of course typecast here to char star, here. So now it might so happen that you get 4 KB right here, but then hey, Q is already overlapping that region, and now you have different dynamically allocated memory regions that are overlapping, and different variables can fiddle with the same memory. Not a good idea. Q might be that part of the program which comes and stores an image here, and ABC might be that part of program which comes and stored like an audio file. So you have stored an audio file halfway through an image file. The audio file is corrupt, the image is corrupt, right? And so you don't want to run into those kind of situations. And this problem is happening because you're doing free more than it's required, right? Double free. So this is the problem of double free.